Hi, good morning, everybody. My name is Robinson.
My name is Qinxi.
My name's Cole.
And we're the Advanced Combustion Technology team. And today we'll be presenting the Methane Hydrate Combustion Analysis device. So this is our team organization. We have split the work of this project into 4 categories. The mass and transfer lead into the combustion, mechanical, and controls. This is a outline of what we'll be presenting today. We will be presenting the background of what our project is focused on, the project goal and objectives, aspects of design, specifications, progress report, the feasibility of our design, and our resources.
Okay, so first I will introduce the background. So first is a chemical formula of methane hydrate, CH4 plus 575 H2O. So as we know, CH4 is the one we need. So in this formula, it shows that methane hydrate is solid CH4, solid phase CH4, getting trapped into in the crystal structure of water. So it's a large, it's a potential energy resource in the future. So I would, all countries they are working on try to use this energy in the future, and as it shows, we have 25 to 157 trillion square cube feet, and 1 cubic meter methane hydrate equals to 160 cubic meter methane gas. But we meet some challenges. First one is it's very difficult to remove the CH4 inside the water in the like normal environment, like in the air, because when we move it to the air, the pressure will drop and then the temperature will increase, so the ice will melt. So some of the CH4 will just goes into the air. So we cannot burn this methane. So our goal is to try to measure try to find the efficiency of methane hydrate combustion. So our objective is to build a MAE0142, which is methane hydrate combustion analyze device prototype. So in this device, we are trying to measure the surface temperature of the methane hydrate. We are trying to measure the core temperature of the methane hydrate, and we are trying to measure the emissions, so that we can know how much carbon we have burnt in this combustion. So we are trying to measure the emission, we are trying to measure the temperature, and also we are trying to measure the mass loss, because the mass loss is water. Water is what we don't want in this combustion. This is our objective of this project.
Some of the aspects of our design, pretty much the big picture of our design is we have to create a chamber in order to pretty much harness the combustion of methane hydrate and to be able to analyze it, analyze its flame temperature, the emissions it gives off, all that stuff. None of this has never been really calculated or really looked at before. Some key features, we'll have pretty much a scale and 2 strain gauges, or a strain gauge and a scale, to be able to measure the water that will be melting once the methane hydrate is combusted. And we'll also measure the actual weight of the methane hydrate sample. We also have to have a steady laminar flow or constant laminar flow to just give enough oxygen to be able to combust the methane hydrate. And a transparent cover to be able to see what's going on. More aspects of the design. You can see the cover. The cover has to have pretty much a sight to be able to possibly in the future fit a IR camera to analyze just some of the flame, flame temperature, like I said before, and all that.
Just to reiterate what my colleagues have just presented, the goal of our project is to analyze the efficiency of a methane hydrate combustion. And as they said, it hasn't been done before, so we had to tailor our specifications to the needs of the researchers to essentially build them a research tool. And as you can see in the specifications chart, we have determined 3 major necessity requirements that would need to be addressed. And that's first, that we need to measure the mass loss, given whether it be the weight lost by the hydrate as it burns or the water produced as it melts. Then we need to measure the surface and core temperature, and we need a device that is able to effectively sample temperatures at a sufficient frequency rate, and that it is easy to mount and essentially portable. Yes. So as you can see, we had a lot of ideas in the beginning. We had, to your right, you will have the first iteration of what would be our design for this device. On the left, you will see a different design, and both were great in their time, but lacked addressing specific needs that the researchers were raising. In particular, the fact that you will mount a measuring tool, analysis tool, and the flame can essentially burn or corrupt your device. So then, we move to the next slide. We came up with what is our final design, and it is essentially a chamber, a cylindrical chamber, with a tapered 90-degree elbow nozzle. And we came up with this design specifically because the chamber, within the cylindrical chamber, you have the possibility of laminar flow if you have the appropriate air supply tool. And for that, we chose a cylindrical tube that will deliver the air through small holes around the diameter of the ring. And with that, we'll achieve a zero pressure disturbance within the combustion of the methane hydrate itself. And then, after the air has sufficiently surpassed the surrounding of the methane hydrate, it will be then accelerated through a reduced nozzle so that we can have a homogeneous air mixture. And this is particularly important so we can have an accurate representation of what's going on in the air mixture itself. So there's that aspect of design, and there's also the aspect that we simply need to protect the analysis devices, such as emissions analyzers and so forth. So the tapered nozzle, you can go to the next slide. The tapered nozzle actually protects the emissions analyzer. And as you can see, that is those are the dimensions of our device, and that is the interior design of the methane hydrate combustion analysis device. Next. So, as of now, we have currently built a prototype that is composed of a 10-inch diameter acrylic cylinder with 2 pieces of galvanized steel, and the first is a reducer from 8 inches to 6 inches, and then the elbow is 6 to 6 inches. And we assembled this not particularly as a final product, but rather as a learning tool to learn how is it that this can better serve as a combustion analyzer. So first we must produce something that is able to facilitate a combustion within the chamber. So our goal is to essentially test other controlled combustions within this chamber, such as a sterno within it, and see if there's sufficient air supply, or if we're able to properly take care of our emissions analyzer. And we did some calculations of what this would cost, and that is essentially what you can see on the top and bottom. In the top you have what we did was a cost diameter analysis, and that is if we chose 304 stainless steel for our product, not the cylinder portion, but rather the reducer and the elbow, we estimated that we would have a linear progression in the cost of materials. That does not include the manufacturing cost. But as you can also see, we backed up our prediction with a separate set of data that gave us a cost versus mass analysis. And the mass of these reducers shouldn't surpass more than 5 pounds. in total weight. So, we go to the next slide. This is our timeline for our project. In the fall, we were gathering information, we were researching, and we were brainstorming. In this quarter, we've been prototyping. And effectively, we have produced a prototype this quarter, and we are moving on to the testing phase. These are some of the milestones that we have achieved. In the fall quarter, we achieved basic design documentation, and then we built a preliminary prototype this month, and then we are on track to building our final methane hydrate prototype in March. These are our resources, and our biggest resource has been Professor John Rankin, who has given us several guiding tips on how to design our prototype and how to go forth about the engineering process. And these are also our images that we gathered. Thank you for your time, and if you have any questions, please let us know.